Alright, today we're going to move on with our study of kinetics and rate law. We're going to go on to section 12.4, which is titled the integrated rate law. And AP Chemistry, as far as the exam goes, the important exam at the end of the year, does involve integrated rate law slightly. Not as extensively as what I'm going to cover today, but it'll just help at the college level and how to use this calculator program that I had you download yesterday, or transfer from somebody else's calculator, the polysci-mult program. So far the rate laws that we have considered basically express the rate as a function of the reaction concentration. So you change the concentrations, and how does the rate change? And you have a data table, and you basically examine that data table and look, if you double the concentration, what does it do to the rate? If it doubles it, does it triple it, does it quadruple it, or does it not change it? No effect, that'd be zero order. But it's also useful to kind of express the reactant concentration as a function of time. And this is a differential rate law basically. And you talk about differentials in calculus, or you will be at some point. So with the integrated rate law, it's going to be a little bit different. It's going to involve the concentration of the reactant this time, versus time. How is that concentration changing over time? Not how is the rate changing, how is the concentration changing over time? And basically what this does is it allows for concentration, and remember, concentration is often measured in molarity. If it's gases, concentration is basically pressure. They're directly related. So it allows for concentration of the reactant. We're always looking at the reactant and how they're changing to be calculated. We're going to do some calculations. And basically at any time. So what I showed you before is we were changing the concentrations, and that's called instantaneous rate. When that's examined right away initially before the reactants are disappearing and the products are being produced. So this is at any time during the reaction, or vice versa, I'm going to say here. You can look at it the other way as well. When we're doing this, and you wouldn't have this on the AP exam, this detailed, but we're going to use table 12.6, which is on page 583 in your textbook. And basically this table, you'll learn how to use it. At first it'll look a little bit foreign, but what you're looking for with this table is a straight line plot, that's a line right there, to determine the reaction order. And in reaction order, again, is it zero order, is it first order, or is it second order? And you can go on beyond that, but we're going to be looking at one reactant at a time, and usually just reactions with one reactant at this particular level. Okay, in that table, you have it in your own text, but here's just a photocopy. And again, it's page 583 in your textbook. And a little bit dark here, but this is rate law. And we talked about rate laws. If it's a zero order rate law, remember rate equals K times nothing. It doesn't depend on the concentration of any reactant. First order, it's rate equals K times the concentration of A, some reactant, to the first, or you don't have to have a value there. And then second order, rate equals K times concentration of some reactant A to the second. Integrated rate law. So it asks to write I ask in a homework problem or quiz or test to write the rate law. This is what I'm talking about right here, like we did yesterday and the day before. Integrated rate law, what I'm asking for is one of these. You don't have to memorize these. I'll give this table on a small quiz or the test. And then I talked about in the notes just now, right here, looking for the straight line plot. So here, how do you get a straight line plot? If you have concentration of A, some reactant, versus time is on the x-axis, and it's a straight line, that is suggesting zero order. If it's the natural log of the concentration of A versus time on the x-axis, that would suggest the first order, and then second order, 1 over A versus T would be second order suggestion. Okay, and then the slope as well. The slope of these lines, remember a straight line is, the equation is y equals mx plus b. So like here, for example, y equals, I'm not going to write it on here, keep it clean, but mx plus your b, okay? And then so here, the slope, the m, or the ax on our calculator, it's going to be, the slope would be negative k. So this is where this is negative k is coming from. And the last line of information here is half-life. How do you calculate a half-life? And we'll deal with these calculations. So here's a half-life equation for 0 order, 1st order, and 2nd order. So keep this handy to your side. Again, it's on page 583 as we go through the notes here. And we're going to use that table. So we're going to go right to an example, and bear with me here. It's going to be a little bit cumbersome and slow at first because this is a little bit technical, but how to use the calculator for this. And we're going to look at sample exercise 12.2, which is on page 573 of your textbook. And I'm just going to turn to 573 myself here. And on page 573, take a look in your own book. The decomposition, it says, of N2O5 in the gas phase was studied at a constant temperature. So temperature is not changing because that can affect the rate, obviously. So you have 2N2O5 gas goes to 4NO2 gas plus O2 gas. And it says the following results were collected. You can see you have a data table there, N2O5, which is in moles per liter, and then time, which is in seconds. Okay, and as I said before, many times, that time is, where is time on a graph? Is on the y or the x? It's an x-axis. So even in your book from previous students, there might be an x above time because that should be on your x-axis, and concentration should be on your y-axis. That's your variable you're looking at that you're changing. Okay. So it says using these data, verify that the rate law is 1st order in N2O5 concentration, and calculate the value of the rate constant. Remember, that's k, where the rate equals negative change in concentration of N2O5 over change in time. So what is the negative for? We've talked about it before. The negative change means that it's basically decreasing. It should go down in concentration. It should be reacting away. And there's a solution they show you there, and you'd have to basically graph it out by hand or Excel or something. But we're going to use our calculators to make this a little bit more user-friendly. So I'm going to write out a list of things that we're going to have to deal with on our calculator, and then I'll show you how to work it. This will take just a little bit of time here, but it's good to have in your notes, and then you'll get to know it secondhand. This would be a good one to keep for a college chem course using this program. Here's how you do it. They might not show you. So first of all, we want to verify as 1st order. So we need a plot of, and if you look back at your page 583 table there, we're looking for 1st order. So here's 1st order, okay? And how do we get a straight line? Plot needed to get a straight line, 1st order. Here it is. This is what we need to calculate to verify that it's 1st order. Or if we didn't know, we would try this. So it's natural log of the concentration of A versus T, or time. So that's what we're going to try. Keep that in mind. So verify, fix this V, as 1st order. So plot of, we're looking at natural log of the concentration of the reactant A versus T. Again, this concentration should be on your y-axis. T, time, is on your x-axis. And for calculator purposes, I'm going to say this right now. The y-axis in your calculator, there's something called lists that you may or may have not used before. This is going to be in a list 2, and the x-axis should be in list 1. Okay. So first of all, for your calculator, I'll show my screen here. Hopefully the whole calculator will fit on the screen. Pretty good there. So turn on the calculator just to avoid problems that may arise here as we go through a problem. It's easier to take care of this right now. I want to make sure you have something called diagnostics on, which is going to be a correlation factor I'm going to be looking for. So that is in the catalog, which catalog is above, it's right here, above the 0, and it's yellow, so it's a 2nd function. So I'm going to go 2nd catalog, and what I want to do, show my screen here, is scroll down all the way to diagnostics, alphabetical it should be. I have quite a bit in here. So there's diagnostics off, and there's a diagnostics on. Make sure your cursor is on the diagnostics on, and then make sure it's going to switch it on, press enter. And it just says diagnostics on. Oh, fix my screen. It says diagnostics on. Press enter again. And you can see it can say done then. So I know it's in there. Okay, so my diagnostic tools are on. Okay. So now I'm going to give you a stepwise process here that we're going to follow through on our calculator. And this is the notes you're going to want to refer back to. So in your calculator, what you're going to do is you're going to press the stat. And we won't do this quite yet. Let's just get it in our notes, and then we'll go through and follow this as like a manual. So press the stat button, and then in stat you want to choose edit. And then in your screen you're going to see here soon when we do this that it's going to be, it should be 1 and then edit. What we want to do is, I'm going to put this off to the side here, is just enter, select that and enter, press enter. And then you're going to see a list 1. On our list 1, that again is our x-axis data, which our x-axis we already said is time. And in a list 2, we want to put our y-axis data. And our y-axis we said was concentration. So once we get to here, this point, we're going to enter data. So just for your note purposes here, let's get enter data written there. Okay. Now I'm just going to say one thing about the diagnostics here for notes, just because I have some space here, put a big star, is that when you calculate this, you want R, I think it's a lowercase r in your calculator, regardless whether it's lowercase or uppercase. R is something called a correlation factor. We've had it once before, it's just how correlated is the data. So want R to be at least 4 nines, okay? And the more nines, it's going to be, 1 would be a perfectly straight line. The more nines, the better. 3 nines can sometimes not be an indication of a good straight line, but 4 nines for sure. So 4 nines for a straight line. And then remember, I pointed this out in that table 583, that y equals ax plus b, or y equals mx plus b, depending on what notation you use for variable. Where a, in this case, there's my a, where a equals slope, and recall that where a equals slope, it's going to be your k value. Okay. All right. Or negative k. Okay. If you look at your data table. So let me grab a fresh sheet of paper here. Get resituated. So now we can start, looking at the data on page 573, your data table. We're going to go through our steps. Have your notes in front of you here. We're going to go through the steps I said. I already turned the diagnostics on. So I'm looking at my sheet. It says press stat. Okay. You won't be allowed to do this on a test, of course. You need to just know how to use this by then. But it's stat edit. And as you can see right here, edit is already highlighted. So that's good. Alright. So stat, edit, and then there's edit highlighted like I said. I'm going to enter. Pressed enter on my calculator. You may have data in these lists. Like these 2 lists are empty. This third list, I want to get rid of that data. So if you scroll up and highlight list 3 or L3, and if I press clear, my cursor is flashing here. It wants to know what do I want to clear. I'm going to press scroll down. There, cleared everything. List 4, I'm going to scroll up and highlight list 4, clear that. Okay. I even have list 5 here, clear that. We're using list 1 and 2, and we're going to tell the calculator to use those lists here in a second. Okay. But we're going to go on. Okay. There's one thing, just kind of thinking here when we get to that point that I'm forgetting on these notes before we go on. Once you get your data entered, I'm going to have to try to fit this in here. I'll just keep continuing down here. Once you get your data entered, you're going to want to press stat again. Stat button. Okay. And then you're going to scroll over to calc, get that highlighted, and you're going to scroll down to linear regression. We're trying to get a straight line, which is should say ax plus b. and then we're going to tell it what we want to test the linear regression on, what data, which will be list 1, our x-axis, and you're going to put comma, list 2, which is our y-axis data. Okay, so there's the complete set of notes for calculator functions. Back to the data table on page 573 for the problem. I'm going to go ahead and enter all of this data. So in list 1 I want time, and time on your data table is on the right side on page 573, so make sure you're getting the 0, 50, 100. So for 0, and I'm going to scroll down, or you can press enter. So I have 0, 50, 100, 200, 300, and 400. Very easy to screw up this data, so if something, double check your data. So I'm just looking at the graph, or at the table in the book, 0, 50, 100, 200, yep, that's what I have. Now for concentration of N2O5, so you test this straight line. We're not looking at N2O5 like the first set of concentration data at time 0 is 0.100. I'm not entering 0.100. I need to enter natural log of 0.100. So natural log is to the left of the 4 right here. Okay, ln, natural log. So I'm going to do natural log of the value, which is 0.100, 0, not that the zeros are going to matter here, but, and close it, enter. Then natural log, remember to hit natural log again, there's natural log showing up, of 0.0707, close it, enter, it calculates it for me. And then natural log of 0.0500, enter. Natural log of 0.0250, enter that. For 300 seconds, it's natural log of 0.0125, enter. And then for 400 seconds, it's natural log of 0.00. Easy to miss a 0 there. Make sure you got the 2 like is shown in the data table. 0.00625. And then enter. Okay? So here's all my data. Here's all my time data on the x-axis. List 2 will be our y-axis. Okay? So looking back at my notes, look back to your notes. We did everything. We have the L1, L2 data in. Now we're going to press stat. Alright, press stat and then scroll over, so right button here, right cursor key, to calc. Scroll down to linear regression, AX plus B, and I'm going to hit enter on my calculator, right there. So enter. Now you need to tell it where to get the data from. Alright, so we're going to tell it list 1. If you look above the number 1, there's an L1. Calculator might be a little bit different, but it's a second function, so I'm going to go second, list 1, comma, make sure you put the comma, separate it out. If you don't put the comma, it's not going to work out for you. And then list 2, and then enter. And there's the data. We could look at the graph, but it should look fairly straight. We'll just look at the data. So R, ignore the negative here, many, 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 many 9s, well beyond 4 9s, at least 4 9s. Okay? Y equals AX plus B. A, your slope, equals negative. It's negative K, remember. 0.00693. So that's our K value. And then we'd have to get the correct units. So I'll set this aside. Okay. So that verifies basically that that is a first order reaction. Why? Because it's a straight line. Okay. And that's all that question is basically asking for. So I'm going to move on to page 574 now, another sample exercise. So turn to page 574, just did myself. So you know where you are in your notes if you're looking back. Sample exercise. This is 12.3. Okay, 12.3, page 574. And 12.3 says, using the data given in sample exercise 12.2, which we just did, calculate the concentration of N2O5 at 150 seconds after the start of the reaction. So I'm looking back at the data table from 12.2, page 573. There isn't a time 150 seconds. Okay? There's no time given at 150. So what we can do is go to our table on page 583, this table again. So kind of open up page 583. There might already be a sticky note there for you from previous class. All right, it's first order. So what is the integrated, sorry about the blackout. First order, so what is the integrated rate law? That's what we're dealing with. Here it is. Okay. So what I'm going to do is rewrite this for ourselves in our notes. I'm going to write this out rather lengthy just for note purposes. It's first order, so our integrated rate law equals, or is, arrow, natural log of the concentration of A equals negative KT plus, look at it here again, natural log of A, now this, A sub naught. This right here, don't believe we've ran into that yet. That means initial. That means initial. So initial concentration of A. All right. So I'm going to rewrite this for our own equation that we're working with. Just looks very similar. I'm just going to plug in N2O5 now. So the natural log of the concentration of N2O5 equals negative KT plus the natural log of the concentration of N2O5 initially. We know what we initially started with. Okay. So now I'm going to plug in data that I know. So we have natural log of N2O5. This is what we're looking for. This is what is the concentration at a certain time. Okay. So we have initially times 0 basically, or the first concentrate, or first time given at least, and then after some time that we're going to find. So equals, okay, equals negative K. All right. So negative K, and our slope, looking at this, says our slope equals negative K. Well, in our calculator, our A, our slope, or M, which you usually call it, is negative 0.00693. So negative K is the negative of this, which is opposite, so it's 0.00693. Now what we're looking at in our equation is we're saying negative of our slope. Our slope is 0.00693. Okay, and what's the unit on K? Per second. If we go back to the orders that we worked on yesterday where he's trying to calculate the unit on K, it's per second, or S to the negative 1 is how you'll usually see it on AP. Times the time, we want to know at a particular time, it was 150 said in the problem, 150 seconds, plus the natural log of the initial concentration. So looking back to the data table on page 573, initially times 0, 0.100. So 0.100, and it's mole per liter. Sorry if that's going off the edge a little bit. Mole per liter. Pull that over. All right. So now, what I'm going to do is say natural log of N2O5, and you might have faster ways to go through this, but just to kind of keep it easy here, is negative 0.0693 times the 150. So on my calculator, it's negative 0.00693 times 150, and that value is negative 1.0395. Okay, and notice per second times second, that will cancel out. So no unit left there. Plus the natural log of 0.100. So natural log 0.100. Enter. So it's negative, I'm going to keep the sig figs the same, negative 2.3026. Okay, and the unit is still the same here, mole per liter, nothing canceled. All right, so now we can add these two together. So we have natural log of N2O5. Again, lots of writing here, but I'm trying to show what I'm doing, getting a better chance of getting points. Don't just write an answer down and get it wrong and lose 4 points or whatever a problem is worth. So I'll add these two together. So negative 1.0395 plus negative 2.3026 is negative 3.3421, and we still have the mole per liter left. Okay. Now the question is, well, how do we get rid of this natural log? Because we just want this concentration. Okay. So is basically, we've dealt with this once. Okay. Is you're going to take inverse natural log here on each side. Or it's like square root. If you had square root here, you'd square, both sides. So the inverse basically cancels out the natural log here. So we have concentration of N2O5 equals the inverse natural log of negative 3.3421. So try that on your calculator, your own here. Make sure you get the same thing as myself or everybody else here. So natural log, we'll say e caret, or e to the power, negative 3.342. Enter. So there's what the screen looks like. And I just did, second function, natural log, which is e to the x. Plug in your data, and it's 0.035, bunch of numbers there. So 0.035366. And sig fig wise, I believe we are looking at 150 seconds. So in 150 seconds right here, 2 sig figs in the answer. If you would have put 3 out of hurrying, and assuming that it's going to be 3 most of the time, plus or minus 1 rule, you would have been okay. So 0.035 unit is still left as mole per liter. Okay? So that's a final answer there. That's what the concentration should be after 150 seconds. So this will, if you're a chemical engineer, let you know how the reaction concentrations are changing as time progresses, where you're at in your process. Okay? So I'm going to deal with half-life for exercise 12.3. Okay, the problem, I don't think the problem asks about half-life, no. So this is being added for your own good, or our own good. This is a first order reaction. So it's first order. So now what is the equation for first order? Look back to page 583. This is a photocopy again. For a first order reaction, half-life is T sub 1 half, equals 0.693 over K. So write that equation down. Okay, and then start plugging in our information. So this is easy, 0.693, and then our K, A equals negative, K, which was negative 0.00693, so make it positive, so 0.00693 per second. All right. So T to the 1 half, T sub 1 half equals, basically you can see what's going to happen here. Okay, this doesn't cancel out. I shouldn't have done that. Okay, but it is 100. This goes into 0.693 100 times. So it's 100 seconds. All right. Sig fig wise, you should have 3 sig figs. You can put a decimal after that. All right. Per second is second. So there it is. All right. Let me see if I want to move on here. Yeah, let's do one more example, looking at time. So clean this up. So we're going to look at sample exercise 12.5 on page 578. So I'm going to turn to 578. You should do the same. Quite a bit here. 12.5 says, determining rate laws again, butadiene reacts to form its dimer, which basically means it's bonding to itself. According to the equation, 2C4H6 gas go to C8H12 gas. So 2 smaller molecules make 1 of the combination of the 2. This is the following data were collected for the reaction at given temperature, and you can see all the data there. You can see time.
The cookie dough delivery for the National Honor Society that was scheduled for today has been canceled.
So there you go. Cookie dough is canceled today if you didn't hear that. So now back to the problem. You have concentration of the butadiene and you have time, X and Y data basically. 3 questions. A is the reaction first order or second order. B, what is the value of the rate constant? C, what is the half-life? So we're going to look at, we'll look at all of that, maybe a little bit more. So we're going to look, blackout, sorry. We're going to look at first order and second order. So it's not telling you to justify or verify. We need to figure out, is it first or second? Or if it just asks, what is the order? You'd look at all 3, first, second, and 0 order. And most often it seems with the AP Chem and problems and whatever, they end up being first order. So I usually say start at first order. If you get 4 9s and you're running out of time, it's a good chance it's first order. If you got time, double check the second order. And if you really have time, go for 0 order. Check them all. So for first order, this is back to page 583. If it's a first order reaction, okay, for a straight line, you have natural log concentration of A. This is butadiene in this case versus time. And we'll look at second order, which will be this. So I'm going to do first order and then second order. Okay. So for first order, for note's sake, let's get this written down. It's C4, sorry about that, H6 concentration versus time. This is your Y or your list 2 data you want. This is your X or your list 1 data. Okay? So let's go ahead and plug that in. You could do list 3, 4, all that, but I clean up lists as quick as I can. So, you know, back to, if you can't remember the procedures exactly, pull out your notes that I just had you right here. I'll pull mine out, and I want to go to stat, okay, edit, lists. I want to clear these lists. I don't want to deal with lists 3 and 4, just, I don't know, I don't want to. So there we go, it's cleared. So now, plugging in data. So in list 1, looking at the data table on page 578 for problem 12.5, our list 1 is time, remember. So it's 0, 1,000, 1,800. So just go and plug in all that data. 2,800. Try this yourself. It's easy to screw up, so you want to make sure you're comfortable and have some practice doing this. 4,400, 5,200, and 6,200. Back up to list 2. Make sure all the way at the top there. For list 2, we are doing natural log of this butadiene. So natural log of the first set of data is 0.01. I'm not even going to put all the zeros. Then natural log of 0.00625. And then natural log of 0.00476. I'm just going to see if I scroll down, will it enter it? Yes, it does. You don't have to hit enter every time. So now I'm at 2,800. Its value is natural log of 0.00370. Scroll down. Next one, natural log of, at 36 is 0.00313. Scroll down. Natural log of, I'm at 4,400, 0.00270. Scroll down. 5,200 is natural log of 0.00241. And then the last one at 6,200, natural log of 0.00208. Enter. Okay. So now I'm going to go stat. I have all my data entered here. So stat, remember. And then calc, scroll over to calc. Linear regression, enter. What list? It's list 1, comma, and list 2. Remember, it's second function list 1, which is number 1, second function list 2, which is number 2. Enter. Calculate that. Spit it out. And I'm going to write down some data here. There's the screen. So our R value, first of all, equals 0. It's negative K, so it's going to be positive. Sorry, thinking ahead here. Our R value, ignore the negative. Correlation factor, how good is the line? It's 0.975. There's a 7 after it, so it rounds it to a 6. Definitely not 4 9s. You think 0.9 is so darn close to 1. It is, but you want to be right there at 1. And just in case, I'm going to write this down. K equals, if this is true, our slope, which is our A, which is negative k, so 2.4. I'll write it all down. 2, 3, 7, 7, 8. Oh, this would have been easy to miss right here. Watch out for that. E means times 10 to the negative 7. That's the values. Okay. I'm going to clear that. I'm going to try second order. So I'm going to go stat, edit. I'm just going to leave this in here just to show you. So I'm going to do list 3 versus list 4 here. So this is like 1 and 2. Okay. So time and then our data. So let's write what we're doing down here. So it's second order. We're going to try now because it wanted us to check whether it's first or second. Second order is 1 over the concentration of A. I'm getting this from, just in case you're wondering, right here for second order. Plot needed for a straight line right there. 1 over A versus T. So 1 over A versus T for note's sake. You know what? Here's the thing. The time isn't changing. The time is not changing at all. So we can do, let's leave that in list 1. We already have it. And let's put this in list 3. Okay? Let's put this in list 3. So this is our y-axis, list 3, versus our x-axis, list 1. And then let's find that data. So in list 3, we need, let's see, 1 over concentration of A. And you probably know this, may forgot, may have never seen it yet, but you don't have to do 1 divided by. You can enter the number. So the number for the first concentration is 0.01000. Put them in. And then x negative 1, that means 1 over, or 1 divided by. So there it is. And then our next one is 0.00625. Next one, inverse that. 1 divided by it. Next one is 0.00476. Inverse that. Next one is, let's see, third, fourth down. I want to see my time. I'm going to put my time so I can see it. I'm having a hard time going back and forth. So at 2800, it is 0.00370. 00370. Inverse that. At 3600, 0.00313. And at 4400, 0.00270. I can see easily forgetting to, oops, what happened there? Clear that. Add a little division sign in there. So this is 4400.00270 inverse. You can easily see I was going to say, forgetting to put that x negative 1 there. So at 5200.00241, and our last value at 6200 is 0.00208. Enter. Okay. So there's our data. So now I'm going to go stat to graph this out. I'm not even going to look at the graph. I'm just going to look at the correlation factor. I'm going to calc. I'm going to do linear regression again. And this time I am going to do list 3. So our time, list 1 was our time. So I want to do list, I'm going to make sure I get this in the right order. It's going to be list 1 versus list 3. This is our x. This is our y. I think that's right. Let's see what happens. So list 1, comma, versus list 3, which is our 1 over concentration values. Enter that, and yep, those are the right numbers. So put this off to the side a little bit. Ooh, hard to see. So our R, our correlation factor right here, is 0.9999936. It just keeps going on. But definitely 4 nines. 4 nines for notes. Means good. Means great. That's what we're looking for. Our K value, K equals, this is our slope, remember. Let's look back at this real quick. Alright, so for, this is important, for second, slope equals just K. So we don't do negative, and it's positive, so it's just K. So K is 0.0612. And for second order, The unit on K, again from yesterday when we worked through the units, it's liters per mole times second. Okay. So what this is saying is it second order or first order? That's what we're looking at. Okay. And it is definitely second order because of the 4 nines. Okay. Sorry about that. So now, to answer the questions, A, is the reaction first or second order? Make sure you answer the questions. So A, first or second, reaction is second order, based on what we just showed there. That's one answer. B, what's B say? What is the value of the rate constant for the reaction? Well, slope is rate constant. Here's our slope, which is K. So K equals 0.0612 liters. You need units per mole second. C, sorry about that. C, it's not a slash, it's times. C, what is the half-life? So we know, pull back page 583, we know it's second order. So we need to look for the half-life equation for second order. T sub 1/2 equals 1 over K, rate constant, times concentration of A initially. You got that not there, initially. So let's write that down. 4 notes again. T to the 1/2 equals, or our half-life equals 1 over K times concentration of A initially. This is concentration of butadiene, C4H6 if you want to plug that in instead, which equals 1 over our K value, it's right here, 0.0612 liters per mole times second times, I should put my 1 right here, concentration at time 0, initial time, it was, looking back to page 578 in the data table, 0.0100. Concentration was in mole per liter. So what we have is liter over liter, mole over mole here. If you multiply these two together, basically they're going to cancel. You still have per second right here. Okay. So when you calculate that out, or T to the 1/2 equals, T sub 1/2 equals, I'm just going to multiply the bottom, then hit inverse. 0.0612 times 0.01000, enter, inverse that, enter. Ooh. Half-life is 1633.9892. Let's do this. 98. Looks like 3 sig figs, so our half-life is 1630. Okay, 1630. Oh, it's slash second. So per second is second equals T to the 1/2. There's that. Okay, I'm going to do one more thing here. I'm going to say, I'm going to put some more paper down for myself. I'm going to add a question. D. I'm going to say the question is, so question, just seems like it could be a good question. What is the rate law and integrated rate law? Could ask both of these. So what is the rate law and what is the integrated rate law? Well, the rate law we dealt with yesterday. Rate law is just writing the expression. Rate equals K times the concentration of the reactant. There's only one in these integrated rate laws for you guys usually, or always. So there's our reactant. It was second order, so you put a 2 there. Integrated rate law. So this is the regular rate law, or expression, rate expression. The integrated version is, look at this, okay? Look at this, and here it is. So integrated rate law, follow it over here is 1 over the concentration of the reactant equals KT plus 1 over concentration of the reactant initially. I'm just going to write it out like that, but I'm going to put my own reactant in. That's all you're doing. So integrated is rate equals 1 over concentration of A, but our A is C4H butadiene 6, which which equals our K value. We could plug in K, we know what it is, but I'll just leave it like that. We don't need it. Times the time plus 1 over C4H6 initially. So that is the integrated form of the rate law. Okay? And again, you won't be using this calculator program on the AP exam. You can't. But basically, I'm trying to teach you some things here that will help you out on the AP exam, I believe. And that is it for today.